All right, so in our next section, 7.5, we're going to take a look at solving exponential and log equations. So a couple of basic guidelines when we're looking at exponential and log equations. When I'm going to solve an exponential equation, one of the most important things is I must isolate the exponential on either one or both sides of my equation before I'm able to take a log of both sides, which is what we're going to do here in a couple of minutes. I cannot take the log of both sides until it's isolated, or things don't cancel out the way that you might think they would, and you'll make mistakes. When you're solving a log equation, you must isolate the log, condense it, rewrite it as a single log essentially on each side before raising both sides with a base of b, okay, to clear the log, or before rolling the log and rewriting it in an exponential form. Okay. So logs and exponentials are inverses of one another. Again, we should have seen this in properties of logs, but just a quick recap: if I have log base b of a quantity and b to the x, those are inverses of one another. And as such, log base b of b to the x, these cancel out, leaving me only with that x in my exponent. Okay, if I have b raised to the log base b of some quantity x powered, the exponential base and the log base cancel, again leaving me with just that quantity, in this case x. Right, same thing goes for our natural logs as well. Here, remember, natural log is just log base e of, in this case, e to the x, and the same way, these are going to cancel and leave me with just x. All right, so same property applies for the natural logs as well, not just regular logs or any log base for that matter. Okay. Change of base formula, right? One of the things, our final answers, just like with other problems, they need to be in a fully reduced form. And for log and exponential equations, the conditions that we're looking at here, they need to be written in a form that I can type into any calculator, right? So the standard here is that it either has to be written using either log base 10 or the natural log. Those are the two that we can type into any calculator, scientific or graphing. While I understand that a lot of calculators have the log base operation or ability in them, not every calculator does. And again, in terms of it being a final answer and fully reduced, you need to possibly, depending on how you go through this process, change the base at the very end of the problem. If you have something that's in log base 2 of a quantity, you're going to have to rewrite that as log base or the log of a quantity over the log of 2, for example, using change of base. Okay, so the log base b of x equals either the natural log of the quantity x over the natural log of the original base b, or the log of x over the log of the original base b. Okay, so remember, the base of my original log becomes the base of my fraction when I use change of base formula, and my quantity goes to the numerator. All right, so I've always remembered this as the base of the log goes to the base of the fraction. Okay, it's an easy way to keep it straight. All right, so first example I've got here is 2 to the x equals 3. And again, remember we talked about it in class. The first thing you always want to ask is there any way that I can solve this by rewriting as like bases? All right, there's, in this case, no way I can rewrite 3 as 2 to some power, at least not some power that I'm going to be able to figure out without a calculator or some other work. So I've got a couple of options. Okay, let me go through the first one with us. All right, right here my exponential base is 2. So the first thing that probably comes to mind right now is, well, why don't we take the log base 2? It's the inverse of 2 to the x. So I need to ask myself, is that exponential isolated? In this case it is. So we're going to go ahead, we're going to take log base 2 of both sides of my equation. So here I'm going to have the log base 2 of 2 to the x equals log base 2 of 3. And when I cancel the log base 2 and the exponential base of 2, I'm left with x equals the log base 2 of 3. Now, if you remember, I said we're not allowed to leave anything in an exponential base other than either 10 or natural log. So let me write this in terms of the log base 10. So I'm going to use change base formula. And again, remember, the quantity is going to go to the numerator. The base of the original log would be the base of the fraction. So here we're going to have the log of 3 over the log of 2. Okay? So I'm going to leave that here just like that for the moment. All right? Let me do this a second way. I'm going to show you a second way to go about this. All right? So again, I said the first option is that we can simply take whatever our exponential base is. I'm going to take the log base that's appropriate, that's going to cancel it out, that is the inverse. The other option that I have is that I can really take any log for that matter. Okay? The two that make sense here are going to be either the log 10 or the natural log, simply because then you're putting it into a form that works for your final answer. But really what I'm going to do next works for any log base that your heart desires. Okay, so let's do the natural log, because I want to show something else here as well. All right, so let's say I've got the 2 to the x equals 3. All right, and I want to take now the natural log of both sides. Once I've taken the natural log, what it's going to allow me to do is use my power rule, and I'm going to bring that exponent down in front. All right, so now again with the power rule, once I've taken the natural log, I can write this as x times the natural log of 2 equals the natural log of 3. Now here, this is pretty much no different than if I had 2 times x equals 3. I would divide by 2 and get x equals 3 halves. No, it doesn't equal 3 halves. However, the natural log of 2 and the natural log of 3 are nothing more than fancy irrational numbers. They're numbers. I can divide both sides by the natural log of 2. And when I do that, we're going to be left in this case with x equals the natural log of 3 over the natural log of 2. Right? And now I've got two different versions of what I'm saying is the same answer. So let's pull up my graphing calculator here and let's check it. Let's see what we come up with. All right? So let's do the first one first. So I have the log of 3. I want to close parentheses divided by the log of 2. And again, I want to close those parentheses. We're going to get a decimal approximation here of 1.585 if we round. Well, let's double check and make sure that when I evaluate with the natural log, I get the same thing. So natural log of 3 divided by the natural log of 2. And well, lo and behold, I get the exact same answer. And just for grins, let's use log base. Right? So if I go into my math menu, option A then is log base. So if I evaluate the log base 2 of 3, I should and better get that exact same answer, and in fact I do. So really what I wanted to do here is show you that there are multiple different equivalent answers that we could possibly come up with that have the same decimal approximation. There are going to be a lot of times where we ask in this unit that you leave something in exact form. Okay, what I've just boxed here are two examples of exact form. One thing I don't want to necessarily see is that decimal approximation of, say, x equals 1.585. Okay, this is an approximation. If we ask for the decimal, that's an acceptable answer. But if we're looking for exact, I'm looking for that exact form, similar to, square root of 2, for example. Square root of 2 is exact. If you take it to 1.41 as a decimal, it's no longer an exact answer. Okay, so let's take a look at my next problem here. All right, so I've got 25 to the 2x plus 1 equals 144. Now, as we showed before, I have two options here, right? I can either take the log base 25 of both sides, or I can take a natural log or a log base 10 of both sides. I'm going to do this both ways again. So for the first way, let's take the log base 25 of 25 to the 2x plus 1 equals log base 25 of 144. Now, again, the nice thing here, the log base 25 and exponential base of 25 cancel out, leaving me with 2x plus 1 equals log of 25, or log base 25 rather, of 144. Now what I need to do is I need to solve for x. So we're going to subtract the 1. Remember, order of operations, exponentials and logs come well before. So here I have the log base 25 of 144 minus 1. One thing that might not be a terrible idea is to use some parentheses, because it's the log base 25 of 144. Closing those parentheses explicitly tells you that that 1 is outside and not a part of the logarithm. When I divide by 2, I get log base 25 of 144 minus 1, all divided by 2. Now, if you throw a box around that and leave that as a final answer, I'm going to take a point off. Why? Because I have a log written here that is not in either base 10 or natural log form. So let me rewrite this in terms, we'll use the base 10 here. So what I'm going to end up with is the log of 144 over the log of the original base 2. So I'm going to have log of 144 divided by log of 2 minus the 1, all divided by 2. This is the final answer, okay, in its exact form. Or I should say in an exact form. This is not the only form. So let me put a little divider in here again. Okay, and I'm going to solve this a second time. And this time I'm going to take, say, the log base 10 of both sides. All right, so I've got my 25 to the 2x plus 1 power equals 144. And again, if I take the log base 10 of both sides, what it's now going to allow me to do then is bring this exponent down in front as a coefficient. Now, I'm bringing that entire exponent down in front. I must put it in parentheses. So here we're going to have 2x plus 1 times the log of 25 equals the log of 144. Now what I need to do from here is I need to distribute this log of 25 to each term inside of the parentheses. In this case, I'm just distributing from the right-hand side. It's fundamentally the same. So here I'm going to get 2x log of 25 plus 1 times, or just simply the log of 25 equals log of 144. Now, log of 25 is nothing more than a number, so I'm going to subtract this log of 25 over on both sides. It's going to leave me with 2x log of 25 equals log of 144 minus log of 25. Now, what I'm going to do last, I have 2 times x times log of 25. The 2 and the log of 25, again, are nothing more than real numbers. So I'm going to divide both sides by 2 log 25. I'm going to divide the entire side by that quantity. And what we're left with then is x equals log of 144 minus log of 25, all divided by 2 log of 25. This is also a final exact answer for this problem. Now you might be saying, they look nothing alike. And I agree with you, they don't. All right. But what I want to show you next is that these are, in fact, one and the same. So if I come back over to the calculator, we're going to start here in the blue on the left. All right. 1 or 2 things that I'm going to need when I do this is I need parentheses around my entire numerator. And let's just deal with the first equation here. That all is going to be in my numerator. I need to tell the calculator that. So I'm going to have open parentheses. I'm going to have the log of 144 divided by the log of 2 minus 1, close parentheses for my numerator, divided by 2. And here I get a decimal approximation of x equals 3.085. All right, now let's take a look at the one in red and see if we get the same. Now again here I need, because I have a sum or a difference in my numerator, I need parentheses around that entire numerator. And in fact, because I have a product in my denominator, I need parentheses around this. Otherwise, it's going to divide it by 2 and then multiply the entire fraction by the log of 25 instead of dividing the entire thing by 2 log 25. Okay, so when I do this, I'm going to open parentheses for my numerator. I'm going to have log of 144 minus log of 25, close parentheses for the log, close parentheses for the numerator, divided by, and I'm going to open parentheses for my denominator, 2 log of 25. Again, close parentheses for the log, close parentheses for that denominator, and we did not get the same answer. So where did I make a mistake in here? I see my mistake. So if we come back over here, right, I went from log base 25 and I accidentally wrote it as log base 2 instead of as base 25. Okay, so let me go back in and let's verify. So I know this 3.085 was incorrect. So let's write down that 0.271 or 272. All right, and let's see in that blue equation, do I in fact get that correct answer? So again, we're gonna have log 144 minus, or sorry, divided by log of 25 minus the 1, close parentheses for the numerator, divided by 2, and there we go. Now we got the correct answer. All right, moral of the story there, okay? Pay attention, all right? Attention to detail here. Anything as simple as, I just wrote down the wrong value from one line to the next. And had I not done this 2 different ways to demonstrate it, I may not have caught that mistake, okay? So pay really close attention. There's a lot of stuff going on here. Easy to make a mistake, okay? But what I want to come back to, the original point that I wanted to show with this was that here we get 2 different, very different looking rational answers, but fundamentally they are the same. Now I could do some serious manipulation and I could make this look very similar, but it's not going to be the same. All right, I wouldn't be able to make it look exactly the same, I should say. All right, they come out to the same decimal, and based on how we do this, you may get different answers. So when you're checking an answer, if you did it in a different way and your answer looks different than what I have in an answer key, punch both of those into your graphing calculator and get a decimal approximation for them. If the decimals are the same, they are the same answer. Okay. All right, let's go on to the next one. All right, so here I have 6 to the 2x equals 10. All right, at this point, it's about as broad as it is long. My recommendation would be to go with the log or natural log when you're solving these. So in this case, I'm going to take the log on both sides. All right, so here we're going to have log of 6 to the 2x equals the log of 10. Again, now I'm going to use that power rule. I'm going to bring this 2x down in front. So we're going to have 2x log of 6 equals the log of 10. And again here, x is being multiplied by the 2 and the log of 6. So I'm going to divide by both the 2 log of 6 on both sides. And here we're going to get x equals the log of 10 divided by 2 log of 6. And again, when and if you would punch this into a graphing calculator, you're going to need parentheses around that entire denominator. Or it's simply going to divide by 2 and multiply by log of 6. When in doubt, use parentheses around your entire numerator and denominator. They can't hurt you, but if you forget them, they will definitely cause some mistakes. Okay. Let's come down, let's take a look at 1 or 2 logarithms. So here I've got log of quantity 2x equals -1. All right, I want to go through, I want to solve this. So I want to isolate the log and I want to rewrite as an exponential, unless it's something that I know how to evaluate right off the bat. So here, log base 10 of 2x equals -1, so we can roll the log, right, if you want to think of it that way. All right, so here we're going to have 10 to the -1st equals 2x. All right, exponent rules 10 to the -1st is 1 over 10 equals 2x. And if I divide both sides by 2, I'm going to end up with x equals 1 over 20. Okay, dividing by 2 is the same thing as multiplying by 1/2, thus the 1 over 20. All right, let's take a look at our next example. All right, here I've got log of 3x plus 1 equals 2. Again, the log is already isolated, so we can go ahead and roll the log, or if you want to think of it as rewriting. So here we're going to have 10 to the 2nd equals 3x plus 1. All right, 10 squared is going to give me 100 equals 3x plus 1. And when I go to solve, I'm going to subtract 1 on both sides. It's going to give me 3x equals 99. And when I divide by 3, I get x equals 33. Now let's come back around and back to exponentials. So one of the more challenging exponentials that we're possibly going to have in this section or in this course is when we have something that looks like this. Here I've got 5 to the x plus 1 equals 2 to the 3x plus 2. All right, so first things first, I am not able to rewrite these bases, 5 and 2, using a common base. So I know that I'm going to have to take a log or a natural log of both sides. Okay, again, you've got some options. You could take a log base 5 or a log base 2 here. Your final answer is going to have fractions within fractions in both your numerator and denominator if you go with one of those routes. They're not incorrect, but they are going to get messy at the end. No matter how we do this problem, it's going to get a little bit messy. So it really comes down to a personal preference. Again, my preference when I do these problems is to use either the log or the natural log. In this case, I'm going to use the natural log just because I feel like writing 2 characters a bunch of times instead of 3 characters, okay? Purely for the sense of I don't want to write more than I have to. So let's take a natural log of both sides. So when I take a natural log, I'm going to have natural log of 5 to the x plus 1 power equals the natural log of 2 to the 3x plus 2 power. Again, now at this point, I'm going to bring both of my exponents down in front. All right, and again, it's the entire exponent. I need parentheses. So I'm going to have x plus 1 times natural log of 5 equals 3x plus 2 times the natural log of 2. And again, now I want to distribute the natural log of 5 and the natural log of 2 into my parentheses here. So when I do that, I'm going to have x natural log of 5 plus natural log of 5 equals 3x natural log of 2 plus 2 natural log of 2. Now, here I've got things that are not going to be like terms, right? But what I do have are 2 terms that have an x in them and 2 terms that have no x's in them. So what I'm going to be able to do, even though I can't combine them, I want to get everything with an x on one side of my equation and everything without an x on the opposite side. So when I rearrange, we're going to have the following. I'm going to have x natural log of 5 minus 3x natural log of 2 equal to 2 natural log of 2 minus the natural log of 5. On the left-hand side now, I've got a GCF here, right? That GCF is x. So when I factor that out, I'm going to have x times the natural log of 5 minus 3 natural log of 2 equal to 2 natural log of 2 minus natural log of 5. And just like before, earlier on, I said when we had x natural log of 2 equals natural log of 3, and we just simply divided because natural log of 2 is nothing more than a fancy number, okay? In this example here now, this natural log of 5 minus 3 natural log of 2 is nothing more than a messy number, so I'm going to divide by it. So we're going to divide by natural log of 5 minus 3 natural log of 2 on both sides. Okay, and what we're going to end up with in this case is going to be x equals 2 natural log of 2 minus natural log of 5 divided by the natural log of 5 minus 3 natural log of 2. At this point, you have a final answer, right? I have something that's written in terms of all natural logs or log base 10. There are no x's contained in the right-hand side, and I simply have x equals some quantity. We have a final answer. Please stop here. Now, if you're sitting there and thinking, well, I'm an overachiever, I can simplify that more. You're right, you can. Okay, I could simplify this. I could use a power rule in my numerator to rewrite as natural log of 2 squared minus natural log of 5 over and natural log of 5 minus natural log of 2 cubed, right? And then I could use quotient rules in both numerator and denominator. I could rewrite that as the natural log of, let's see, we're going to have 4 over 5 over the natural log of 5 over 8. Okay, I could simplify this and then even furthermore, I could work backwards with the change of base formula here and rewrite this as the log with base 5/8 equals or of 4/5. Okay, please don't do that. All right, as soon as you get to this point here where I've got x equals and a quantity that's all in terms of natural log or log base 10, all right, there are no x's contained within it, stop here. Because if you're right at this point and you continue on and you make a mistake, I'm going to take points off for it. Okay, even though you were correct at this point, if you continue on past here and try and simplify farther, I will hold you accountable for mistakes that you make. Okay, so please, as soon as you get to a final answer, put a box around it, stop. Okay, that's where we're going to stop with our notes for today. All right, the one thing I would encourage you to do, go through, I want you to try one or two of these problems. So I'm going to make one up for us right now. So I want you to solve 4 to the 2x minus 3 equals 6 to the x plus 1 power. So I want you to go through, I want you to solve this, right? And when we come in to class, we're going to take a look. We're going to see what everybody got as an answer. We're going to look at what different forms of the answer we got, and we're going to check to see if we have any mistakes or anything that we need to talk about. All right? So have a good night, and we will see you guys tomorrow.